précédence, en fait, de présentation sur la mécanique quantique. Donc, c'est quelque chose d'assez... Ouais, que la théorie physique, c'est une des théories rares qui a créé beaucoup d'échanges au-dessus. Donc aujourd'hui, en fait, et demain, il y aura tout à fait une sorte de synthèse, de réflexion sur l'interprétation que la mécanique quantique aura. Donc c'est un projet que Rival va présenter un petit peu sur le projet de livre qui a plusieurs présentations et des articles assez propres là, qui sont les interprétations et les fondements de la mécanique quantique. Comme vous savez, c'est une théorie qui introduit pas seulement certains savoirs, mais aussi comme principe d'un cercle qui est apparu même comme principe sous-jacent. Donc, ce qui est important, en fait, j'insiste surtout qu'il faut respecter le temps, car on va essayer de rattraper de façon bien, car il y a beaucoup de conférences, et en même temps, en fait, le temps découvre pour les pauses de café ou d'autres. Donc ça, on va essayer de... Donc, surtout les téléphones qui sonnent, machin, on va essayer de ne pas le mettre en marche, couper ça, pour éviter. Donc il doit être enregistré. Donc en fait, normalement, en principe, vous pouvez regarder les conférences plus tard avec tous les détails. So I will back to the English version. So thanks very much to be here with us, because it's very wonderful thing. They have changed today about quantum mechanics, one things. You know what about things. So we have the pleasure to have you here in Paris-Saclay University. Because really is the thing, because quantum mechanics is very important thing and theory, but it's still a question about interpretation and foundation for quantum mechanics. Still there are many questions about. There's no question about the real theory, but about interpretation. That depends maybe, the question is there are no foundation of universal principles as we found in relativity. Anyway, we have 2 days to discuss this issue. So thank you very much to be here and to deliver. So we spent 2 days. We have 3 professionals who will represent the department and the laboratories from the university. And we have already from Paris and present the issue about cultural things. So I will leave it to Oliver to actually think about what to present this book.
Okay. Good morning, everybody. We are here today to celebrate the publication of the Oxford Handbook of the History of Quantum Teleportation. The motivation to write this handbook, which is there, derives from the fact that most of the available literature on this topic, many times it lacks the diversity of perspective, the diversity of interpretation, and the diversity of different solutions for foundational issues. Then we have tried, we were inspired. I remember that the first time I talked about this project, it was with Frank Leroy, and he told me, this is again a new Max Jammer book, remember? And I told him, no, it's not a new Max Jammer book, because we no longer have Max Jammer with his capacity to write this wonderful 1974, The Philosophy of Quantum Mechanics. Then we have tried to bring together a number of different physicists, philosophers, historians of physics, but to keep the same spirit of the 1974 book by Max Jammer. Which means a book with the diversity of interpretation, the diversity of perspective on the quantum mechanics problem. Now, this conference was possible for a number of reasons. We were the organizers of this conference. The main idea came first from Jacques Sassignac, and I would like to invite Sassignac to say a few words mainly about the people who helped us to organize this conference.
Thank you. There are many people. I would like to thank the organizer and the department. That, for me, it's a great pleasure to be here in Paris 7 and then Paris Diderot and then Paris-Saclay, and so we are in the spirit of the old Paris 7. That means that we have many different disciplines: physics, cosmology, the department of RPT, mathematics, and philosophy, the department of Aspect. I want to thank many people in this department. But anyway, first I want to thank the young people who are very, very helpful for us. I hope Laura Soulard, Jordan François, Yves Debout, Philippe Vincent, Gauthier de Pancourt, Laura Sasséo, Cécile Barbassou, Valentine Biget, I hope I please all, and the different department, director of physics and cosmology, and so. And I can invite you to speak in behalf of this department. Thank you.
Anyway, we have to thank very much Alain Aspect to take time to participate in this day of day to see, because that's a reference today, as you know, about quantum mechanics. What Alain adopted the project of realization of the question of band equality. That's very important thing in the quantum mechanics, because they have before and after. And that's a good point. But we see Alain pushes something very anticipated with quantum mechanics. What the sense of quantum mechanics, and show exactly what we mean. I think today we have some word about it. So I want to thank very much. I thank Aurélie also from maybe taking some word from Paris about cultural thing. And what to Jonas, please.
Okay, so thank you very much to be here. Welcome everybody. And I would say on behalf of the physics department, I'm more than delighted to welcome and even host this, how could I say that? It's a 2-day journey over 1 century, probably, of debates, discoveries, technological breakthroughs. So I think all of this, of course, don't have so much button, so it's all this just gathered in this book. So gathering mathematicians, physicists, of course, but also historians and philosophers. And I think you are in the place to be, because, as you said, we have a long historical track of working together and interdisciplinary work in this University Paris-Saclay. And also the right place, because here, in the building of the physics department, it's not just ABC, which is the lab of Antoine Kouchner. Will say a few words after that, because working on astroparticles and cosmology, of course, everybody can understand the importance of quantum mechanics, but also MGQ, which is a lab dedicated to the quantum field. And I would say that illustrating this book by Bell's work, I think a lot of people here are working today just to get entangled particles with very small devices now. And also teaching this. I mean, it's now in work with students in this place, but also all these people are working in the same building with people coming from the historical field and the philosophers. So I think nowadays we are very focused on technology, of course, but sometimes lacking this old-fashioned work between disciplines. But this is alive here, and thank you for coming and make it still alive.
Thank you.
Good morning, everyone. I'm Antoine Kouchner, the director of the APC laboratory. And APC stands for Astroparticle and Cosmology. So it's a pleasure to be associated to this event. We had a logo, the first page, so thanks very much. We are hosted in the physics department, indeed. So the lab is mostly from the 2nd to the 5th floor, and 2 buildings, A and B. So if you want to walk a little bit during the break, you're invited to come and look and discuss with the people. So I would like to say a few words about the APC laboratory. It's actually, we're studying a lot of things. We have 5 thematic groups or departments. And so the first one is high energy astrophysics, where we study cataclysmic universe, essentially. And we are a lab with a lot of experiments. So we have experiments in satellites on the ground, and also even deep in the sea, where we try to catch elusive particles like neutrinos, and to study the universe properties. The second department I would like to mention is the cosmology one, where also we have a lot of experiments going on with foreseen satellites and also experiments associated to the ground, where we want to study the dark universe and the infancy of the universe as well. We have a special group that is focusing on gravitation through the study of gravitational waves, and this is also on the ground with the Virgo detector and the LIGO detector, but also with a space mission that is foreseen to fly at the horizon of 2030, which is called LISA, and this is a very flagship experiment for us. And then we have a particle department, particle physics department, where we study particle physics properties that could be the Higgs, but also neutrinos, and we would like also, of course, sometime at some moment to discover the nature of dark matter. And then we have another department, which is the theory one, and here we have theorists, colleagues that are working with us, experimentalists, or sometimes working on their own to try to, to understand and pin down the universe. So all this together, it's the physicists, and then we have heavy technical departments that are key for us in developing our instrumentation to study the universe. And so altogether we are about 220 people hosted in this building. And of course we have strong interactions with the other laboratories hosted in this building. And this is how we get to discuss and to participate, and this is very likely. So it's a pleasure to have you here today and tomorrow. And I hope that you are going to have a very fruitful time and discussion. Thank you.
I'm sorry, I'm going to speak French, but Joseph m'a fait la gentillesse de me proposer de dire un petit mot en tant que néophyte, je dirais, en théorie quantique. Un petit mot sur les liens entre art, culture et science, peut-être physique. Donc je le fais avec beaucoup d'humilité et vraiment avec un grand plaisir, un grand honneur d'être avec vous ce matin. Évidemment, ce n'est pas à vous que je vais expliquer que la physique quantique est une des immenses avancées de la pensée humaine. L'histoire culturelle du quantum, qui est moins familière au commun des mortels, est bien documentée. Peu après 1927, le mot, les termes associés au quantique, tels que la complémentarité, le principe d'incertitude, ont commencé à apparaître dans les disciplines universitaires en dehors des sciences. Et même les fondateurs de la physique et de la mécanique quantique ont appliqué ces termes à d'autres domaines, la justice, le libre arbitre, même les sentiments que l'harmonie. Le rôle du hasard et de l'incertitude, principe d'incertitude, apparaissent dans la culture populaire. Cette terminologie est aussi une terminologie utilisée par les artistes, dans le monde des films, dans la sculpture, dans la poésie. Le monde quantique n'est donc pas seulement un lieu où des expériences scientifiques complexes sont menées par des spécialistes qui s'expriment en langage mathématique, mais aussi un territoire pour l'imaginaire et pour l'imagination de tout un chacun. Explorant le monde quantique, de possibilités infinies, un monde d'enchevêtrement, de symétrie significative entre la science moderne et la science dure en quelque sorte, et les sciences humaines. Littérature, poésie et physique quantique se croisent dans l'interprétation d'une réalité physique. Les physiciens, comme les écrivains, comme les poètes, posent une même question. Savoir, au fond, regarder le monde, l'observer, puis l'interpréter et le transmettre dans un langage, peut-être un langage mathématique ou un langage artistique ou poétique. Ils s'appuient tous deux sur cette perception métaphorique et sur des processus herméneutiques de traduction en récit. John Stuart Bell lui-même, dans sa discussion sur l'interprétation de plusieurs mondes, écrivait « Le physicien théoricien diffère du romancier en pensant que peut-être l'histoire pourrait être vraie. Mais au fond, on peut se demander si l'histoire racontée par le romancier n'est pas elle aussi peut-être encore plus vraie que la réalité telle qu'on l'aperçoit. » D'autres disaient que les théories des physiciens et les fictions littéraires ont beaucoup en commun. Les deux postulent des mondes hypothétiques. Les deux sont parfois jugés par leur degré de vraisemblance à ce que nous considérons comme le monde réel. Certaines hypothèses scientifiques sont valorisées parce qu'elles peuvent être vérifiées, tandis que les fictions sont souvent valorisées dans la mesure où elles nous semblent conformes à l'expérience d'un lecteur de ce qu'est le réel. C'est ce que disait Dennis Bodenkamp. Quand on parle de physique quantique, on met généralement l'accent sur des phénomènes qui semblent contre-intuitifs à la pensée prétendument rationnelle. Évidemment, la fameuse expérience que tout le monde connaît du chat de Schrödinger, la superposition du vivant et du mort. Les dualités, la dualité homme-particule, l'état de superposition, l'intrication, tout ça est un territoire immense pour l'imagination de n'importe quel béotien dont je suis. Ces choses sont passionnantes parce qu'elles nous font rêver, parce qu'elles sont exotiques, mais aussi parce qu'elles correspondent à une réalité qui, au fond, nous échappe, mais que nous cherchons à cerner peu à peu, par petites touches scientifiques, petites touches impressionnistes que sont l'art ou la poésie. C'est aussi, évidemment, de manière épistémologique, la distinction entre le moderne, qui serait identifié à une forme de rationalité un peu positiviste, celle des Lumières, une science qui poursuit la connaissance objective par des moyens empiriques, solides, stables, et le postmoderne, qui serait identifié à un relativisme épistémologique, en accord avec une conception de la connaissance plus humble, non pas absolue, mais conditionnelle, comme le démontre la physique quantique, c'est-à-dire au fond dépendant de l'observateur et de l'observation. Et c'est conscient de l'importance, de l'impact de toutes ces avancées scientifiques pour l'ensemble de la société, pour l'ensemble évidemment aussi de la culture scientifique que la mairie de Paris et toutes les instances de politique publique sont soucieuses de développer, que en tant que directrice des affaires culturelles de la ville de Paris, je suis absolument ravie de pouvoir participer à l'organisation de cette rencontre entre vous tous, scientifiques éminents, ici à Paris, dans ce très beau quartier nouveau, universitaire et scientifique du 13e arrondissement. La ville de Paris a tenu à apporter son soutien à cette démarche qui vise à rapprocher, à intégrer la science dans toute sa diversité et aussi la culture, puisque vous y êtes sensible, et en particulier à la musique. Nous espérons que le book et le colloque d'aujourd'hui vont continuer de motiver les générations futures pour approfondir l'étude de ce merveilleux domaine, infini domaine de connaissances à construire, qu'est le quantique. Et maintenir vivantes et riches les discussions sur ces fondements. Bonne journée à tous.
So, we would like to invite Alain Aspect to take the floor. And we have no word to be thankful to you. Take time to open this conference for us.
Don't introduce me because he's the best expert of my scene.
Good.
Don't introduce me.
Okay, thank you very much, Madam. So, you have this if you want.
I use this one. There are people online,
Yeah.
so I will try to use.
Jack, can I take it? The front is the here.
Yes, but then
Yeah.
I'm going to see.
presentation. I am impressed to be in front of people who are expecting to improve their understanding of the epistemology of quantum mechanics. I'm absolutely not going to speak about epistemology. I'm going to speak about non-locality, and I think it's a question for people who think about epistemology to understand the status of non-locality, and I will develop just my point of view of an experimentalist about what is the status for me. For me, it's a useful image, and I'm going to explain you that. But of course, before doing that, I will start with a standard and general presentation to know what we are talking about. I like to start with this. Today, everybody or many people speak about quantum technologies, and if you ask yourself how did they emerge, I think that they emerged with Einstein and Bohr. The problem is that when I was expecting to see the arrow here, but I have to move here. Okay.
Sorry, could you please share your screen?
Yeah.
The what?
Share.
Could you please share your screen? Thanks
We
a lot.
do not see the screen on Zoom.
Someone is trying to do translation. Tu dois poser.
Non, c'est partager l'écran.
Oh non, d'accord.
Non, mais moi je saurais faire.
Il faut cliquer en haut sur reprendre le partage. La flèche verte.
Reprendre le partage.
Voilà. Allez-y, ça.
Mais je pense qu'on ne peut pas avoir exactement la copie de l'écran. Il y a d'abord le mode présentateur. Je préférerais avoir une copie plus d'abord le mode présentateur. Et comme ça, on le verrait.
Ça, c'est pas simple.
Voilà, reprendre le partage. Un mot, flèche verte, voilà. Flèche verte. Ah ben non, les gens qui sont à distance, il ne faut pas commencer. Il n'y a personne qui indique. Votre partage est en pause. Appuyez sur le
reprendre le partage.
On va essayer de le reprendre.
Il est toujours en pause. Moi, non, mais c'est il faut avoir un mix toujours dans une conférence comme ça. Gauthier, c'est pas un mix.
Non, c'est pas comme ça qu'il faut faire.
Non, il va falloir faire. Non, mais on l'a fait déjà. On a tous fait 3 fois, ça ne donne rien.
Excusez-moi, je pense que vous avez besoin de... You have to make Dominic co-host, I think, before you can share his screen.
What?
I think you have to make the speaker co-host before you can share the screen. None of us on the Zoom can see the screen.
Partagez l'écran en bas à droite. Partagez l'écran ici.
Peut-être Joseph, votre partage, non?
Ah, ça,
ça marche les autres. On va connaître pourquoi.
ça marche.
Vous êtes en train de partager.
Merci. Je veux passer. Voilà.
Enlever la barre du haut.
Bon.
Juste cliquer sur les.
Tu peux déclencher le problème. Remets-le à 0, s'il te plaît. Bien, donc je recommence. Vous m'entendez à distance? Or do you hear me, people online? No.
Oui, bien sûr.
Okay.
Yes.
Thank you. Okay, so I'm not going to give an epistemological talk. It's a talk about physics and just the way I use the concept of non-locality. So quantum technology, how did they emerge? There is a discussion between Einstein and Bohr, and in addition, Schrödinger adds his grain of salt, and with all of that, the conclusion was that entanglement is amazing. And then they had to wait another 39 years, excuse me, and John Bell came, and to make a long story short, the conclusion of John Bell is entanglement is different of work, different of the way people were thinking about quantum mechanics, and in particular, the linearity of quantum mechanics. Everybody was thinking of the linearity of quantum mechanics, but I am not sure, and probably people had not realized that the application of this linearity of quantum mechanics about two entangled objects at a distance really raised a completely new question. Another 20 years, and Feynman in 1982, there is this famous paper of Feynman, which is simulating physics with computers, in which Feynman first acknowledges that he had missed the importance of entanglement. If you read lectures on physics, which was published in 1960 or 59 or 60, Feynman addresses the question of EPR and say EPR is nothing else than what we have seen about interference of a single particle. And in 1922, Feynman said, oops, I missed the point. And entanglement is really something different. And Feynman being Feynman, as soon as he says this is new for me, he invents a way of using it, and he raises the basis of quantum computing. So what I am going to show you, I'm going rapidly to rephrase the EPR reasoning in the version of Bohm, which is the one that everybody uses, and the one that you need to have to derive Bell's inequalities. Many people miss that point. You need to have dichotomic variable. Can be a spin one-half, can be polarization of a photon, that you need dichotomic observables. So I'm going to derive that, and then we will go on until Gautier stops me. So Einstein was asking the question. We all know that Einstein was annoyed by the probabilistic character of quantum mechanics. Of course, Einstein had no problem with statistical physics. You know his famous paper about Brownian motion. But he thought that it was a convenient tool, statistical physics, but that the bottom had to be non-probabilistic. And so he was asking the question, is it possible to explain the probabilistic character of quantum prediction by completing quantum mechanics at an underlying more precise level of description, and you can call that level supplementary parameter, hidden variables, etc. It's clearly the same kind of reasoning as to say, if I have a Maxwell-Boltzmann distribution for the molecules in this room, in fact, I think that each molecule has its own trajectory, etc., and that the statistical description is convenient, but is not fundamental. And so Einstein tried to find situations in which the very laws of quantum mechanics allow one to precise, for instance, position and velocity better than what is allowed by the Heisenberg relation. Okay? And what I call Heisenberg dispersion relation. By the way, I don't like the more principle of uncertainty, because it's not a principle. It's a consequence of the mathematics. It's mathematical relations, dispersion relation, which are a consequence of the principle, does not derive from anywhere. Okay. And so Einstein tried to find situation in which the quantum calculations allowed you to precise position and velocity better than allowed by this. He first tried with single particles, Gedanken experiment. It was in the Solvay conference in 1927. He said, oh, look here, you can define the velocity and the position better than allowed by Heisenberg relation, but at the end of the day, or at the end of the night, next morning, Bohr would come and say, no, 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 this does not work. And we can say that Bohr always replies satisfactorily to Einstein in this Solvay conference. But in 1935, Einstein thought to the famous Einstein-Podolsky-Rosen-Gedanken experiment with two entangled particles, and not only two entangled particles at a short distance, but two entangled particles with separation. And then, in my opinion, everybody can make his own opinion, because the papers are published in a physical review. It's very easy to find them. In my opinion, the reply of Bohr to Einstein is considered as valid only by people who have already totally adhered to Bohr philosophy, okay? Okay, so what is the experiment? Most of everybody knows this experiment, but I just precise. I have a photon U1 going to the left, a photon U2 going to the right. They don't have the same color, so don't look for anything like indistinguishability in this experiment. And you make here a polarization measurement, which is a dichotomic observable. The polarizer can be oriented, and you have an orientation defined by the unit vector A. And when the polarizer is oriented on A, you can get either result +1 associated to the polarization along A, or result -1 associated to polarization perpendicular. Same thing on the second polarizer. And if now you have many pairs and you repeat, well, one pair at a time, but you repeat the experiment many times, what can you obtain at the end? You do statistics and you obtain probabilities. So you can obtain the single probabilities to get +1 or -1 here, but much more interesting, of course, the joint probability. Probability to get +1 here and +1 here, and you call it P++ of AD, because you have to say what are the orientation of the polarizer. So this is just a description of an experiment. You don't need any quantum mechanics to. Well, you need a little bit of quantum mechanics to accept the idea that a photon is a particle, but it could be spin 1/2. Well, you need also. Okay, okay. It's not yet EPR. EPR is if you have a state describing the two particles, which is like that. And even people who don't know very much the formalism of quantum mechanics can easily understand what it means. XX would be a pair of photons polarized along the direction X. YY would be a pair of photons polarized like that. XX plus YY is an entangled state, which means that I cannot develop it mathematically and present it as a product of a certain state for the first photon and a certain state for the second photon. It's impossible. Don't think that it is, for instance, at 45 degrees or something like that. And at this point, it's almost as surprising as the Schrödinger cat, which is both dead and alive, except that there are only 2 photons, and in the Schrödinger cat, yeah, there is more than 2 photons, of course. But conceptually, it's the same kind of problem. How can we think of something which is both this and that? That's a problem for you. So once you have that, it's an elementary exercise in quantum mechanics to calculate the various probabilities. And the single probability are 1/2, which means that whatever the orientation here, you have 50% chance to find +1, 50% chance to find -1. It's just like a game of tossing a coin. Same thing on the other side, but when you calculate joint probability, you have something which is very interesting, because here, for instance, if I make the angle between the two polarizers equals 0, then the probability P++ is equal of 1/2. And I claim that there is a total correlation. You are going to say, no, 1/2 is not total. Yes, 1/2 is total. Why? Because the probability to have +1 is 1/2. And if you have the joint probability to have +1 and +1 is also 1/2, it means that the conditional probability to have that one, if you have this one, is 100%. And if you are not yet totally convinced that it is an interesting situation, the cross probability P plus minus is 0. So it means here it looks totally random, here it looks totally random, but if you have +1 here, you have +1 here, if you have -1 here, you have -1 here. Okay, so what do I have now? Well, I have already explained that, so let me continue. So, the reasoning of Einstein, Podolsky, and Rosen at this point consists to say, we know that what we found here is the same as what is found there. And the reasoning of Einstein, Podolsky, and Rosen was to say, because we know that And because it is at a distance, the relativistic argument is crucial. Because the two measurements at a distance, if we know for sure that they are the same, we don't need to do the measurement here. We know in advance what will be the result there. And they concluded that quantum mechanics has to be complete. Okay. And so I want to insist that relativistic separation is really at the root of Einstein-Podolsky-Rosen reasoning. If the two particles were on top of each other, nobody would. Well, I don't say nobody would care, but it would not be, and the EPR reasoning would not work. The EPR reasoning is based on relativity, and I have two citations, one from Einstein in the famous book Philosopher Scientist. On one supposition, we should, in my opinion, absolutely hold fast, the real factual situation of system S2 is independent of what is done with system S1. And the reason why he say that is because of relativity. And Romain and Aronoff have something similar, but let me go on. Bell theorem. I like this photo. I like also a similar photo which is on your handbook, because this experiment is my experiment. So, you know, Bell is really a personality. First, he shows that the von Neumann proof that you cannot have hidden variables is false. There are not many people who have found a mistake in von Neumann, okay? So it was a good start. Then he writes his paper, okay, in which he will find that there is a way to show a contradiction between quantum mechanical prediction and completing quantum mechanics with hidden variables is to assign a property that he calls locality to the hidden variables. So the idea is the following. In order to explain this correlation at a distance, you just admit that the two photons share a joint property from the start, okay? And this joint property that we call lambda, that he calls lambda, will determine the result of the measurements. And then it's not complicated to understand that it's a good way to understand correlation. It's an image which is used all the time in science. For instance, if you have two twin brothers, similar, same, I don't know how they say, same twins, okay, homozygote. If you observe, suppose they are born here, and then one goes to America, one goes to Australia, and when the age is 20, you observe the color of the eyes. They have the same color of the eyes. No surprise, they have the same chromosome. Maybe one develops genetic disease, and the other one will develop it. No surprise. So to understand correlation by joint property from the production of the two particles is very natural. And so one may think that it is a good way to understand quantum mechanics. But at that point, Bohr disagrees, and Bohr disagrees because he, I would say after reading him so many times, I think that he had the strong intuition that quantum mechanics would fall apart, that the safe consistency of quantum mechanics would be ruined if he would accept that. But he did not demonstrate it. It's Bell who demonstrated that, so we have to give the credit to Bohr, that he certainly had the intuition, and we must give the credit to Bell that he demonstrated it. And Bohr thought that quantum mechanics was complete, and as soon as you introduce supplementary parameters, you complete it, because in quantum mechanics, all the pairs are described as the same state that I've written already, 1/2 of Eclair, while here you add something different for each pair. The lambda is different for each pair. Okay. So an example. No, not yet. So the formalism, he uses the formalism in which you have the function capital A dichotomic, can take only value +1 or -1 to describe the result of the measurement at first polarizer. Capital B describe the result of the measurement at the second polarizer. And of course, you must have a distribution for the probability distribution for the supplementary parameter lambda. And once you have that, you can calculate the correlation coefficient, which takes this simple value. It's a usual definition, the average of the product minus product of the average, and you normalize, but it turns out that the product of the average is 0, and when you normalize, it's 1. So it takes this simple form. And I like to show this very simple example. It's an example that any of us would think of after thinking more than 5 minutes, okay? Maybe some of us are faster and would find it in 2 minutes. You assume that it means something, that the photon has a certain polarization. And then if the polarizer is like that, you get +1. If it is like that, you get -1. And you must have a frontier, because once again it's dichotomic, and you put the frontier at 45 degrees. And that's all. And with that, so the function which is here, I'm sure that Jean-Pierre has already seen that it does the job, okay? And when you use that, you find the red line, which is not bad from the quantum prediction. It gives full correlation at 0 degree, full correlation at 90 degree, and it's not so far. And so the question, you may think, okay, with a little more sophistication, you are going to be able to find a model agreeing with quantum mechanical prediction at all orientations. And Bell's theorem just says, no, it is not possible. So Bell's theorem, so no local hidden variable theory in the spirit of Einstein's idea can reproduce quantum mechanical prediction for EPR correlation at all orientations of polarization. This is how it works. There is a quantity S, which is associated with 4 measurements. You take 2 direction A and A prime, 2 direction B and B prime, and you make measurement for AB, AB prime, etc. 4 possibilities. And then you write this strange combination, 3 plus, 1 minus, 1. Why 1 minus? I don't know. Just as a question why John Bell was a genius. He had a good idea. Okay, and then I have here a demonstration which is extremely simple. It does not take more than 2 minutes, but I will pass, and if you want, I will show you in private, or maybe if you ask questions later. And then the demonstration is really high school mathematics demonstration. But Bell theorem says that this quantity cannot be bigger than 2, cannot be less than -2. And if now you take the quantum mechanical prediction, which is written here, for this angle, here is pi over 8, pi over 8, and pi over 8, cosine of 2 times pi over 8 is 1 over root 2, so you have 1 over root 2, 1 over root 2, 1 over root 2, and here is 3 pi over 8, you double, it's minus 1 over root 2. And so you get more than 2. This is Bell theorem. You cannot mimic, reproduce the quantum mechanical prediction at any angle, and in particular, you have a counterexample. You have a situation in which you cannot mimic quantum mechanics with a local hidden variable theory. Okay, so it turns into an experimental equation, but before going to the experiment, I want once again to, not once again, I want to think for 1 minute about where we are. We think of completing quantum mechanics with supplementary parameters carried along by each particle. This is what is some kind called Einstein local realistic view. Why? Because Einstein clearly thinks that when you have a system which is localized in space-time, when Einstein writes space, it clearly means space-time. When you have a system which is localized in space-time, he thinks that in that volume of space-time, you have all the properties that will determine any measurement you will do on that system. So you have the lambda here, it will determine everything. Okay? So this is called Einstein local realist worldview. Okay. And you, in order to demonstrate in addition, so you first assume that, so you introduce lambda, or the simplest way to render an account of Einstein position is to introduce a lambda. And then the locality condition that Bell found necessary to to find the contradiction is the fact that the result of the measurement here cannot depend on the orientation here, which can be written mathematically as saying that the function capital A cannot depend on B, and reciprocally capital B cannot depend on A, and of course also you need to have the way in which the pair are emitted does not depend on the orientation of the polarizer. All that makes sense, but what Bell emphasizes in the conclusion of his paper, and this sentence changed my life, because when I read that, I said, this is what I want to do. Bell said, if you could change the orientation of the polarizers while the photons are in flight, then the locality condition would no longer be a reasonable hypothesis. It would become a consequence of relativistic causality. Okay. That's it. So now, experimental test. So an experimental test is possible, but one must find a situation where the test is possible. I showed you one with the photon polarization and the angle pi over 4, but this was found by Clauser, Horn, Shinoni, and Holt. The initial paper of Bell was more a paper of a theorist, okay? So Clauser, Horn, Shinoni, and Holt made a proposal for a real experiment, and now I'm going to give a very fast overview. How am I doing with time? I like to say that there are 3 generations of experiments. The heroic pioneers in the 72, 76. There was first Clauser in Berkeley, Clauser and Friedman, and Pipkin and Holt in Harvard. Clauser found a result in agreement with quantum mechanics and violating Bell's inequality. Pipkin and Holt found a result not in agreement with quantum mechanics and agreeing with Bell's inequality. But it rapidly became clear that the experiment of Clauser and Friedman was a better experiment in the following sense. You could really change many parameters and observe how it evolves. In the Pipkin experiment, it's an experiment which is frozen. The only thing that you can do is repeat it, or maybe kick it. But there is no parameter, no knob you can turn, okay? So from this point of view, the Clauser and Friedman was more convincing. And after a few years, there was a clear trend in favor of quantum mechanics. Clauser repeated the experiment of Pipkin and Holt and found quantum mechanics. And Fry in Texas in '76 did an experiment in which there was for the first time a laser. The signal to noise ratio was better and the results were about the same. All these experiments, after a few years, were reasonably convincing in favor of quantum mechanics, but all these experiments were significantly different from the ideal scheme I have described on which the theories discuss. And this is the reason why I embarked in '75 into experiments in order to develop experiments with scheme closer and closer to the scheme discussed by theorists. And then there was a third generation. I will say a few words about that. It started in the end of the 80s. Okay, so just to give you an idea, the experiment that started in '75 was carried out in Orsay. The first one was in '81. So you see the source is very complicated. We have 3 lasers, an atomic beam, etc. It's really a complicated experiment. But the idea is to use this radiative cascade. These are levels in calcium. These had been identified by Clauser and Friedman. And the point is that Clauser and Friedman could not excite easily that level here. And when I started thinking about that source, there were fantastic experiments here, close to here, by Cagnac, Rembert, and Birabin, about the possibility to use 2 photons to excite directly a state like that. So I could, not this one, but I could apply this concept of 2 photon excitation to excite directly that state, selective excitation, and when the atom is here, it has no choice. The only thing the atom can do is to send the two photons which are here. It was not the case in Clauser and Friedman. There were many parasitic routes. And to go from here to here, you have two possible paths. And as usual in quantum mechanics, when you have two paths, you must add the amplitudes. Here it's written with polarization, with circularly polarized photons, but then you change bases and you obtain the state you want. It's wonderful. And it was indeed wonderful. I give here the numbers. 100 coincidence signal in 1 second. And you have to know that in this kind of experiment there is absolutely no noise. Because of this narrow correlation, you eliminate all noise. So the only uncertainty, here is a real uncertainty, is a statistical uncertainty. And so it's just a great number, Poisson law. So if you accumulate for 100 seconds, you have 10 to the 4 event, and the precision is 1%. In less than 2 minutes, you have 1% precision. It was fantastic. It was order of magnitude better. And for Clauser, it took days. And for Frey also, it took hours and hours. Here, a few minutes, and it was working. And so this was, so we were using pile-of-plate polarizer, which is only one-pass polarizer, which is annoying, but it was like the previous one. But we tested something which is interesting, the so-called Fourier hypothesis. There were people who would say, okay, entanglement, we understand entanglement. And as a matter of fact, if you want to understand the levels of the helium atom, you know there are 2 electrons in the helium atom. If you want to understand the structure of the level of the helium atom, you have to think of entangled state. But it was at short distance. So some people would say, okay, entanglement exists at microscopic distance, but not at macroscopic distance. And so there was the question, what is the scale? They scratch their head and say, okay, the only available scale is the coherence length of the photon. And the coherent length of the photon was 1.5 meters. So I pulled the polarizer at 6 meters, and it was still violating Bell-Simpson. Okay. But it was the only new part of that experiment, except for the best, for the better signal-to-noise ratio. Then comes the first new experiment. As I told you in previous experiment, people, and us also for the first one, had only access to that result, and the other polarization, the other result was absorbed. So you don't have access to the minus result. And what do? Well, theorists are smart people, and they tell you, look, you are going to measure without any polarizer, then you measure with the polarizer, and the difference is the minus result. It's not stupid, I mean, but it introduces some new hypotheses, and for this reason, it was much better to be able to develop an experiment like that. I think that it is now long ago, so I can say that I have to bribe some people in the physics research labs to construct for me this polarization split specifically, because nowadays you can order it, okay, you have on shelf, etc. But at that time, they calculated it, just to give an idea, there are 34 layers of dielectric with wave control, index of refraction, etc. When I ask how much I owe, they say, you cannot pay, it's too expensive. So I gave them a few bottles of wine. So this is, you see, there are 2 detectors, one here and one here. And I just emphasize the fact that each detector has a lead shield, etc. It's dozens of kilograms. Okay. The beauty of this experiment is the following. You just put the system as it is. You choose an orientation A and orientation B. You have a run of 100 seconds. During that run, you have 4 results. N plus plus, N plus minus, N minus plus, and minus minus. And that's all. No calibration. You just write this ratio. So in the numerator, you have similar result with the sign plus, cross result with the sign minus, and the denominator is just the sum of the 4. It's self-calibrated. That's the beauty of that experiment. Frank encouraged me very much You remember, Frank, you were a fan of this scheme. And the result is unbelievable. Well, we have to believe it, but the result, let's say, is beautiful. The green curve is a prediction of quantum mechanics taking into account all the small defects. What do I call 5 minutes déjà? Oh, okay, I rush. You asked me during the coffee. Last experiment, we want to change the orientation of the polarizer while the photons are in flight, and turning something like that, which weight of 30 or 40 kilograms, we cannot do it. So the idea was to introduce here switches able either to let light go in this direction or to redirect it. Here you put a second polarizer, so now you go from A to A prime, back to A prime, just by switching here. Same thing on the other side. We did the experiment. It was not as impressive as the previous one. Anyway, we violate Bell's inequality by 5 standard deviation. I forgot to say that with 2 paths, we violated it by 50 standard deviation. But here, okay, 5 standard deviation, signal was not as good, etc., etc. For the first time, Einstein causality was enforced. So third generation experiment, they are able to they were able to produce photons in well-defined directions so that they can feed them into optical fibers, and then optical fibers you can go at hundreds of meters like Zeilinger, or even tens of kilometers. And this Giesen in Switzerland, he uses a commercial network of Swiss Telecom, their optical fiber, and he can go at 30 or 40 kilometers. It's amazing. Okay, so nowadays we can consider that all the loopholes have been closed. You know, there is a lot of discussion. I will not speak about it, but I emphasize the fact that I've written a news and views, but not in Nature, because I had some conflict with them. So I've written it from the American Physical Society, Physics. It's online, and I have a long paper about how to discuss these loophole-free experiments. Okay. So what can we conclude? Well, we can ask Einstein. I want to emphasize this point. So you may be surprised. So we are going to ask Einstein about the failure of his vision. Yes, Einstein made reasoning ad absolute. He said, if I was not right, this is what you would have to swallow. And these are the words of Einstein. Either drop the need of the independence of the physical reality present in different parts of space, or accept that the measurement on S1 changed instantaneously the real situation of S2. This is called quantum non-locality, but it can also be called quantum holism. Quantum holism is an important concept for the following reason. Quantum holism means that there is more in the two entangled particles than in the sum or reunion, call it as you want, of the first one and the second one. And these are the root of the power of quantum computing. But what I want to develop in the last 5 minutes is, is the fact that non-locality is forming a very useful image for my intuition. So I show you what I mean. Well, first this I pass. But now the only conclusion that I have here is that I can describe what happens with standard quantum mechanics by considering that I have first a measurement here and then a measurement there. And then the description using the projection, postulate, etc. is the following. Here, until the last moment, I can have either plus or minus. But if I have plus, then instantaneously, the photon on the other side adopts the same orientation. And if I have minus, then at the moment of the measurement, instantaneously the second photon adopts that. This is that image that I use for my intuition. Okay, so let's expand that. And so I want to apply that to quantum cryptography. The problem of cryptography, not quantum at all, there is an absolutely reliable method which is the following. Alice and Bob, where is Alice? Alice and Bob on the other side want to communicate and there is an awful spy, an eavesdropper, who is here. And the absolutely safe method consists of having a similar random string of 0 and n for Alice and for Bob. Alice uses this random series of 1 and 0 to encode, and Bob uses the same one to decode. So the problem boils down to distributing to Alice and Bob the same random series of 0 and 1 without the spy being able to observe it. And to make a long story short, this is how it works. Alice and Bob do measurements. Sometimes the polarizers are along the same direction, sometimes they are not. But they do the measurement with entangled photon, and they note everything, okay? And then later, with the public radio, Alice will say, this was my orientation, and then Bob say, okay, this one we discard. This was my orientation, and Bob say, oh, I use the same one, so we keep it. And they can do that exchanging radio. The point based on non-locality is the following. Is there anything to spy here for the eavesdropper? No. Because if you believe in my story, okay, that until the last moment, nothing has happened. It's only at the last moment when the measurement takes place here that it is decided whether it is +1 or -1. In between, there is nothing to spy. And so, by this intuitive image, I know immediately why this method, which is the Eckert method of quantum cryptography, is good. Then I can develop calculation, etc. Immediately, by that image, I know that I know the value of this. And just to say that the Chinese have put a source of entangled photon in a satellite, and they are able to distribute entangled photon at more than 1,000 kilometers. I just want to say, wait, one word, wait, it's enough. One word about my intuition based on non-locality for quantum teleportation. Quantum teleportation, of course, is not Star Trek, is having a state here transported, teleported onto an object which is, and this is very surprising because you know that there is absolutely no way to fully know a quantum state. If you have only a single object, you can only have one projection on something, you cannot have the full. But here, we are not going to have it, we are just going to erase it here and transport there. So I pass, I make a solve, if there is an no-cloning theorem, etc. I just go to the end to explain you what is the point. What is the point? Well, the idea is the following. I have here the photon of which I want to transport the polarization. I have it interacting with one of two entangled photons. I have a pair of entangled photons. It interacts by a beam splitter and then a so-called Bell state measurement. Don't ask me, but it's only 4 results possible, so you can encode the result, which is now classical, because you have a result, okay? And you can encode it on 2 bits, you send it here, and then you operate the transformation on the second photon, and now the state which was initially here is transferred until the other one. So this is the scheme. But if you believe in the story that when the measurement is done here, instantaneously the photon U2 which is here is transformed, you have a problem. Because this takes time. It's a classical channel. So you have to put the second photon on hold, waiting for the classical signal to arrive. And this is what Nicolas Gisin has done by adding a long optical fiber, but most of the people who claim that they have done quantum teleportation don't do that. They cheat, in a sense, because they post-select only cases where you don't need to transform. Read the paper. Frank Brooks' idea is surprising. I found that because I was writing a problem about quantum teleportation for my students at Polytechnic. And by writing the problem, I realized this point. I wrote to the author of the teleportation paper, and they confirmed. So you mean, and this tells you one thing. Not too many young people here. When I have many young people, I say something. There is one big advance which is absolutely demanded in quantum technology, a good quantum memory. If you have a good quantum memory, there are very beautiful things you can do, including having real quantum teleportation. So, okay, conclusion, blah, 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 blah. Non-local image, this, in relation to epistemology, non-local images give fruitful intuition for quantum technology to be checked by the standard formalism of quantum mechanics. I don't say it's real or it's not real. I know it is useful for my intuition, and you can debate it, you who are thinking of epistemology. Thank you very much.
We have time just for one or two questions. Maybe two questions and then. Okay, you first.
Yes, I would like to make a remark. I think if you really think about Einstein's objection, I think it had very little to do with determinism, always to do with
Absolutely.
locality. Always to do with locality. In 27, he gave this example of a hole, and then there is an hemispheric screen, and the particle is detected at a precise point. And then it says, if the wave function is the complete description, then the wave function collapses on the point when I do the measurement. So it instantaneously becomes zero elsewhere, and that's non-local, already dead. And at that time, in that discussion, Bohr said explicitly that he did not see what the point of Einstein was. So I think, and you can see that in 49, you can see that in 35. I think at every stage, Bohr never understood the objection of Einstein. Oh, you can reply, of course.
What you are describing is about one particle.
Yeah, but with the trouble
Let me with one particle, there is a bomb hidden variable theory which is able to describe everything, which is not the case for the two particles, because in the two particles case, the bomb theory has non-locality. So, but with the experiment you describe, with any experiment with a single particle, you can always say, oh, the bomb theory is able to describe it locally. Second question. Second question.
Okay, no question. Thank you very much. Let us invite Fred Laloye to take the floor.